Okay, so we're going to continue on with section 7.8. This is part 2 for improper integrals. So last time we just talked about the definition of the improper integral. So the idea is I want to think about it as a limit instead of trying to evaluate an integral at infinity. We're going to see, I'm going to do a bunch of examples of this first type of improper integral. We're going to see what kinds of functions um, have finite, you can interpret it as finite areas or which ones don't. So you'll remember last time we talked about 1 over x squared. So 1 over x squared had finite integral on 1 to infinity. So I was able to integrate it from 1 to infinity, and I got, remember, 1. So let's look at this example. Determine if the integral 1 over x from 1 to infinity dx converges or diverges. Okay, so in order to do that, we're just going to jump in and try and evaluate it. So we have the integral from 1 to infinity, 1 over x dx. And again, I know a lot of you would want to just at this point jump to the antiderivative evaluated at 1 to infinity. You can't do that. We have to think about this as a limit. So this is the limit as t approaches infinity, the integral from 1 to t, 1 over x dx. So the idea is, I let this, instead of taking the top one to be, infinity, I take it to be some variable number and let that variable go off to infinity after I've integrated. Okay, so then this is equal to then the limit as t approaches infinity. Let's find the antiderivative for this. We know this one. This is ln of x evaluated from 1 to t. I'm going to drop the absolute value because we're talking about positive values here. So we don't even need to worry about the absolute values there. So just evaluate now. So this is the limit as t approaches infinity. And then we have ln of t minus ln of 1. This is the limit as t approaches infinity, 1 over t. Sorry, ln of t. I don't know why I took a derivative there. So ln of 1 is 0, so that's what that is. And that's why I only have ln of t now. So if you look at the graph of ln of t, as this goes off to infinity, this is infinite. Can do better than that. There we go. That's a little better. So this integral then diverges because it doesn't yield a finite value when I take the limit. So let me just point that out. 1 over x squared, I was able to find that. So we had the integral from 1 to infinity, 1 over x squared dx. This was 1. And then the integral from 1 to infinity, 1 over x dx diverged. So we're gonna eventually going to do an example. We're going to do an example of how to figure out, for what values. So which of these, what values of exponent do these things converge or diverge? Okay, so let's just talk about what this means. So if you really think about this, if I have the graph of 1 over x squared, it's going to look like this. So this is y is equal to 1 over x squared. And 1 over x is going to do something like this. So they both go off to 0. You'll know if you take the limit as x approaches infinity, these are both going to 0. So what you can think about, this meaning is 1 over x squared goes to 0 in such a way that, when I add up all these rectangles, I'm getting such small numbers that they aren't changing anything. I'm always, when I add them all up, I get 1, and then no matter what I add to it, doesn't change it. Whereas 1 over x doesn't go to 0 fast enough, so I get an infinite area in that case. The integral diverged. So that's just, something to think about. So they both go off to 0. one of them was finite, the other was infinite. So probably not expecting that if this is your first time seeing this. So let's do the next example. So we have the integral, integral from minus infinity to 0 of x e to the x dx. And so one thing you should notice is, as this goes off to negative infinity, this thing is going off to 0. So we'll expect, hopefully this converges to something. Okay, so this then is, so remember, don't forget to write it as a limit. First step is always to write it as a limit. Limit as t approaches minus infinity. The integral from t to 0, x e to the x dx. So you'll need to know how to integrate this, obviously. What is this going to be? So you need to do integration by parts. I guess I can, write it all out since you have your exam on Thursday. So u in this case will be x, dv is e to the x dx, du is dx, v is e to the x. So then this is the limit as t approaches minus infinity, uv, x e to the x. Evaluated, so it's a definite integral, so I evaluate it, go from t to 0, minus the integral v to u, minus e to the x dx. This is still t to 0. So we just keep going. So the new step here is just to add this limit, and then we do the integral. So this, when I plug this in, I'm going to get minus t e to the t. The first term 0, check it out. Again, you should be, as I'm going through this, you should have some scratch paper checking my work. A couple people do, a couple people have caught mistakes. And then this integral is then going to be e to the x, evaluated between t and 0. So we just keep going. Limit as t approaches minus infinity, minus t e to the t, minus e to the 0 is 1, minus e to the t. And simplify a little bit, so this is limit t approaches minus infinity. So minus t e to the t minus 1 plus e to the t. Okay, so now we're going to evaluate this limit. So one thing you should notice is the last two terms we can evaluate directly. So as t approaches minus infinity, so as t approaches minus infinity, negative 1 stays the same, e to the t. So e to the negative really large number is 1 over e to the really large number. So that's going to be 0. So the negative 1 is going to 1, e to the t is going to 0. The only thing we need to figure out is limit t approaches minus infinity, negative t e to the t. I can drop the minus sign because I can always bring limits or pull constants out of the limit. So let's evaluate this one. So if you think about what's happening, so this as if, if I were doing, if I was thinking about what type of limit this is, negative infinity times 0 indeterminate. So so t is t goes to minus infinity goes to minus infinity, e to the t goes to 0 as t goes to minus infinity. So this is an indeterminate limit. So we have to use L'Hopital's rule here. So we don't have any other tools available to us yet. So this is limit as t approaches minus infinity. You'll remember the trick for this one is writing 1 as the reciprocal. So this is t over e to the minus t. So if you think about what this one is, then this is negative infinity over, as t goes to minus infinity now, this is going to infinity. This is infinity over infinity indeterminate, and we can use L'Hopital's rule now. So L'Hopital's rule only works for infinity over infinity indeterminate types. So then this is the limit as t approaches minus infinity. And I just take the derivative of the top and bottom. Derivative of the top is 1, derivative of the bottom is minus e to the minus t. And as this goes off to negative infinity, this is going, so 1 over, so this is, so let's figure out what's going on here. Just be explicit with everything. So this is negative e to the t. So bring it back up into the numerator there. So as t goes to minus infinity, this e to the t, if you look at its graph, if you need to do that, this is going to 0. And I'm going to pull that together. So what I have now is I have this one was going to 0, that one was going to 1, this one goes to 0. So what I have is, I'll erase that, because if you're looking at my notes afterwards, it might be useful to not have that already there. So what I have then is the limit as t approaches infinity, minus infinity, of negative t e to the t minus 1 plus e to the t. So when I do this, I'm going to get minus 1 in this case. And that's my final answer. So again, what we're doing now is we're evaluating these infinite integrals, and what we're finding is we have to do this limit, and because of that, we're going to have to remember all our old tricks for evaluating limits. And I'm gonna, so how much have I done? I'm gonna stop this one here because the next example is kind of long. I'm trying to keep these around 10 minutes. So we're gonna continue on with this. There are 2 more examples for this type 1 integral, and then we'll move on to the type 2.